Welcome to Spring LIB.
Okay, so this problem is kind of a doozy for being the second problem. I think that there's a lot of details to this problem, and I mean, so much so I was reading through the book at the relevant section. This section, let me scroll to it. It's like the middle, section 4. And they go through the derivation for getting the intensity. And I noticed a mistake where they get the electric field added. So if you haven't read it, pause the video and read through it and come back. But they basically derive the intensity, and then they say, okay, these omega, these time dependent terms. So like in equation 5c, this time dependent term, you can just ignore it and just say because as you average that, it goes to 1. Intensity is an average measurement. So if you're averaging the time-dependent term, that goes to 1. And then that's how they get their answer. But actually, I would go to half. Sine squared averages to 1/2. So there's actually like an error in the book, and you can Google double-slit formula to figure this out. But to confirm this. But anyway, just stating this is kind of maybe a more difficult problem, at least to make your answer nice and simple. So anyway, the approach I took was kind of modifying this phasor diagram in figure 13. So I'm just going to draw the original, basically, if you look at it, there's 2 phasors, equal length, and then there's a phase difference, an angle difference between them of delta, and then you want to get the vertical projection. This is figure 13 again. And so, I mean, it's a pretty simple geometric problem, but again, getting it down to a nice form, I think is challenging. My approach was just doing it totally geometrically at first, but then I had trouble getting my answer down simply. But yeah, so what I want to do then is I want to take the approach of, let's see. So like they come up with this E theta. And so they have, so here it is. I'm going to kind of reproduce it, I guess. So that's our total phasor length. And then here's our E theta. Was that E theta or E naught? E theta. So here's my theta. And then and that came from like adding both of the vectors up. So like the first vector was something like this that represented the first slit electric field, and then here's the second one, and then this angle between them we said was delta. And then basically we just add the vertical projections here to get E naught. We already kind of know what this is in like a super simple form because E theta, because the book derived it. So I was thinking just to modify, basically all we want to do is add this. So we're trying to increase the length of one of the electric fields. And so basically that's going to amount to increasing the length of one of these. And so let's think about how we can modify that. So let's figure out how much are we increasing this length by. So we just to kind of make sure I'm really clear on my game plan. This is what we have. We're trying to add these 2 vectors up, or this is the original problem is adding the 2 vectors representing the electric fields of either slit, and then they're the same length because they're the same electric field. Now we have a new electric field, so we're going to make one of these longer. So I'm thinking, why not just make the bottom one longer? So I'm going to make it So here's, let's say that's the original length, and then I'm going to increase the length. Let's figure out how much I want to increase the length by. So if I'm doubling the intensity, I know intensity is proportional to electric field. So if I want this to go up by 2, this has to go up by the square root of 2. And so basically then we need to add the square root of 2 minus 1 in length. So this is maybe the additional length, let's say. So that's the square root of 2 minus 1. Right, because we want to figure out the difference, because we want to figure out how much to add to this original vector, which originally has a length, let's say, of E naught, which is the notation in the book, E naught, E1, and E2. So we want to increase it to square root of 2, so that means we need to add the square root of 2 minus 1 times E naught to it. Hopefully that was clear. I know that was slightly scattered, but yeah, this is the basic idea. And then we can keep the other one the same. So I kind of ran out of room, but I'll just do this one in red, and then maybe I'll do this in red to make it clear. So this is just going to be the same thing. And so again, now this angle is going to be a little different. So pretend those connect. And then again, what we really want to find is this vertical projection. And so the vertical projection is the sum of this plus the sum of this. So here's like our additional one. Ooh, I should do that like in a different color. So here's like the additional electric field, square root of 2 minus 1 times the original. And then, yeah. So our goal, basically, we want to just add this length plus this length plus this length, but we already know what this length is, or the sum of the red and black length. So we just need to find this green length and add it to that, and to get the total electric field. And then we'll go ahead through the process of squaring it to get the intensity. Okay. And so, great. So basically now what we want to do is, so let's go ahead and pull from the book the formula for the electric field. So the original electric field is going to be equal to 2 E naught cosine of delta over 2, and then times this sine omega t plus phi term. Oh, phi over 2. And then now we want to add this additional term. So we need to add this green length right here. So that's just going to be E naught times, so sorry, not E naught, but so it just be kind of by basic trig, we have the hypotenuse of this green triangle, and we want to multiply by this sine of this angle. This angle is omega t. So it's going to be plus the square root of 2 minus 1 E naught sine omega t. Great. So now we have a formula for the total electric field, this projection here, and to get the intensity, we want to square it, or at least to get the profile of the intensity. So I'm not going to worry so much about the prefactors, because I mean, there is a difference. There are prefactors between an intensity and an electric field, but I'm just going to say intensity is proportional to E squared. And so really what we want to do is just square, and we also want to time average it. And so that means that anything that with so let's kind of review time averages. I'm going to put this like up here just to try to keep this as organized as possible. So sine squared of any angle oh, I shouldn't reuse theta. So let's just say sine squared alpha, where alpha is just any angle. The average of that, the time average of that, oh, actually, you know what? Why not just use omega t? Just so the time dependence is totally clear. Sine squared omega t, the average of that is equal to the average of cosine squared omega t. And then that's equal to 1/2. And just Google that if you don't know it. And then Google how to do it. I think it would make this video extremely long if I did it out for you. And it's very commonly found on the internet, and you can probably convince yourself too. And then the average of cosine omega t, sine omega t is equal to 0. Again, just Google it. But I mean, you would be evaluating an integral of that from 0 to 2 pi over one period. 0 to 2 pi over omega. Okay, so we'll keep that in mind. Kind of put this in our little back pocket. So here we go, back pocket stuff. And there's also a trig identity, but I'm just going to write it out. So, okay, now we want to square this whole big thing. So square the first term. And then I'm going to do the time averaging at the same time so I don't have to write as much. So squaring all of this, squared, squared, squared. And then this averages out to 1/2. So it's times 1/2. But then I'm going to just do the math and make this 2. Again, just to try to keep this as unmessy as possible. Square the last one. So squaring this prefactor gives you 3 minus 2 square root of 2 e naught squared, and then another sine squared omega t averaging, and then that gives you 1/2 time averaging. And finally, the big old term is this product between the two. And okay, so I'm going to start a new line for this term. So this is plus this whole term. So double the product. So it's 4 times e naught squared cosine delta over 2 sine omega t. And then I'm going to use the formula for adding angles. And so I'm going to simplify this sine omega t plus delta over 2. So it's sine omega t cosine delta over 2. I can't believe I still remember that formula. Plus cosine omega t sine, oh my god, 5 over 2. Great. And then if you are imagining kind of foiling these out, you're going to multiply a sine omega t against a cosine. And then that's going to kill this term, because remember that the time average of sine omega t cosine omega t is 0. So we can just kill this term. And we can kill it so much that I'm just going to erase it. Again, just because, I really don't want to use another page. Hopefully I don't have to. Let's see. And then this sine times sine is going to average to 1/2. So I'm just going to erase that. And then I'll make this 4 2. So 2, and then now we're left with these two factors multiplied over this huge space. So that's just going to make that squared, and then I'll just kill this off. So wow, what a little messy poo. So I'll just simplify it. I got some room. So these two are the same term. So that's going to be 4 e naught squared cosine squared delta over 2 plus this term 3 minus 2 square root of 2 all divided by 2, and that's times e naught squared. Yeah, so maybe there's a simpler way to do that. I'm not sure. but it qualitatively looks correct that you're never gonna have a zero because you're never gonna have the two sine waves perfectly canceling out. So there's gonna be a floor sort of to the intensity represented by this term, and then here's the oscillation on top of that floor. Yeah, so that's how I approach this problem.